Hello, you might be wondering, why would I ever need to create another collision video? Well, back when I was a wee little programmer, I wasn't thinking about having to run this game on different computers or anything performance related. In the first video, I used a method called SAT. Pretty much all you need to know about this is that it's great for high FPS and big objects. But things start to go bad when the FPS gets low or the collision objects become too tiny or thin. I know that not all computers come with amazing specs, and I know that someone out there has a dusty old computer that's been sitting in the attic for years that could barely open a Chrome tab without sounding like a rocket ship. We could see that when running the game on a lower end machine, the FPS seems to drop, and if it drops too low, the collision stops working. But why is this? Well, in real life, movement is continuous. To move my hand up here, my hand has to go through every position in between. But in computers, it works a little differently. Computers have frame rates. I'm sure most of you know what this is, but it's really fast images that change multiple times per second to mimic movement. This means that movement can't be continuous. If you look closely, the objects make really small jumps every frame. This is what it would look like to move every frame if the frame rate was 240 FPS. But imagine we lower the frame rate to 60 FPS. The object still has to travel the same amount of distance in 1 second, but it has less frames to do so. So the object now has to make bigger jumps. For simplicity, let's say that the distance the object has to travel is 60 feet over 1 second. So if there's 60 FPS, then it will travel 1 foot every frame. If there's 240 FPS, then it will travel 1/4 of a meter every frame. But what if we lower the FPS all the way down to a single frame per second? Now the object has to move the full 60 feet in a single frame. That's a pretty big jump. This new method completely removes this problem. It's called Continuous Collision Detection, or CCD for short. My collision system is a little unique, as it will only ever need to test a moving circle collision object with a static polygon collision object. Although dynamic circle versus circle or polygon versus polygon works similarly, it is still a slightly different approach. To see how this method is accomplished, let's take a look at this polygon. The old method looks like this. The circle would move in jumps every frame. Then its position at the end of the frame would be calculated against the collision object and pushed back accordingly. But like I mentioned earlier, the object moves in jumps. This means that if the object was tiny enough or the FPS was low enough, the object can just jump over the collision. When we test the collision now, we can see that the objects aren't touching. This is like running as fast as you can, going straight through a wall. That just doesn't make any sense. The new method works very differently. Instead of looking at the end position, we take a look at every continuous position through the frame. Since we are checking the collision against a circle and polygon, we do something called polygon inflation. This is where we inflate the edges of the polygon by the size of the radius. If we don't do this, then the circle's radius wouldn't matter, and it would only push back the center of the circle. But the character isn't one-dimensional. He's got depth. The algorithm looks something like this. We look at each object and each of their edges, then at the edge's normal vector, or which way it's facing. If it's facing away from us, or it's the other side of the collision, then we just don't worry about it. But if it's facing us, then we get to use this equation to find the closest distance on the line to the point. Then we do some more fancy math to find how much the character is moving towards the edge. Then we do the negative distance divided by this value. We make the values negative because in games, the normal vectors always face outwards. This means that when the player moves towards an edge, the dot product will always return negative. In math, this means that the vectors are going in the opposite direction, which is true. But opposite directions in video games mean collision, so we have to flip these values. After that, we are left with this value called the TOI, or time of intersection. This value is why we did all the math. It's pretty important. Its use is to tell us what time in between the frame the player has passed the collision. If done correctly, this should range from 0 to 1, 0 being the start of the frame and 1 being the end of the frame. So imagine there are 2 points. There's the start position at the start of the frame, and the second one is where the player has moved at the end of the frame, which is the player's location plus the move vector. I know that this is taking a lot of imagination, but also imagine that there is a wall. For simplicity, let's say that the character's radius is set to 0 and the start position of the player is 0, 0, and the end position is 2, 0, while the wall is perfectly vertical at x equals 1. we can use some of our intuitive brain to see that it will take perfectly half a frame to hit the wall. Instead of using the old math here that would just brute force the way to the end position and worry about the collision afterwards, we can now set the location of the character to the hit location of the wall. This is done simply by setting the character location equal to the start location plus the move vector times the TOI. This will perfectly set our location to the edge of the wall. This works fantastically. The program now stops the player from moving when they hit a collision object, no matter the FPS or the size of the collision. But there are still a few problems. Instead of using a simple box, let me distort it a little. Now when the character moves and hits the wall, we can see that the player just stops. But in video games, when you hit a diagonal wall, you don't just stop, you also slide. Right now, the movement feels very sticky because we are only setting the location to the hit point. But we also need to use the remaining time to calculate a little bit of slide for the player. All we have to do is get the hit normal, multiply it by the remaining amount of time, or 1 minus TOI, then add it to the character's location. Now we have a little slippy wall. But there's still one more problem. What if we have an object that looks like this? The problem here is that the program only calculates one collision edge at a time. And once the player is inside the collision, the TOI will now not be in the range of 0 to 1 because they have passed the edge. So the character will just slide right through the wall. The best way I found to fix this was to have multiple checks on the collision per frame. Fantastic! We finally have a method that works if you ever need to run the game on a Samsung smart fridge. You can easily do so without the fear of passing through objects. Well, that's all for this video. Bye bye! Ah, not this again. Luckily this time I added an exit.